In this video, we're going to talk about displaying quantitative data with Stemplots. Also called a stem and leaf plot, a stem plot looks something like this, where there are two parts. There's a stem and a leaf. Very adorable, if you ask me. The stem is this green part right here, so that's the beginning number. And then the leaf is all of the digits that would come after it. So for example, let's make sense of this. What we're looking at is an example where we have data on the resting pulse rates or beats per minute of 19 middle school students. So we've got numbers as low as 68 and as high as 120. So we take the first digit, so that's 6, 7, 8, 9, 10, 11, 12, and then every digit after that goes on the leaf side after this long line here. So 6, 8 represents 68, and that 6, 9 represents 69, and for example 9, 0 represents 90, and then 9, 6 represents 96, and so on and so forth. What's really important in a stem and leaf plot or a stem plot is the key. So this key says 8 line 2 is a student whose resting pulse rate is 82 beats per minute. Just in case there are people out there that don't automatically know how to read a stem plot, which might have been you before this video. And here are 4 major steps on how to make a stem plot. So you make the stems. So that's that left-hand side, if you're thinking of it like a list. You write the stems in a vertical column with the smallest on the top, so it goes smallest to greatest. You draw a vertical line at the right of this column. Do not skip any stems, even if there is no data value for a particular stem. So let's say you go from 60 to 120, and you don't have an 80 anything. So you still write 8, there's just no numbers to the right of it. And then you add your leaves, which you write to the right. W-R-I-T to the R-I-G-H-T. And then you order the leaves from increasing order, as we've seen. And then you add a key. That's really important, because that identifies the variable and explains what the stems and leaves represent. And it's basically useless without that key. So let's practice making our own. So this example is called Wear Your Helmets. So the problem is many athletes and their parents worry about the risk of concussions when playing sports. A football coach plans to obtain specially made helmets for his players that are designed to reduce the chance of getting a concussion. Here are the measurements of the head circumference in inches of the 30 players on the team. So what we're going to do in this example is make a stem plot, and then we're going to describe the shape of the distribution and see if there are any obvious outliers. All right, let's start with making that stem plot. So here's all my data points. They're not in any particular order. So what I like to do, as usual, is identify the smallest value, so that's 20.8, and then identify the highest value, which right next to it is 25.6. So that means that the stems, or the left-hand side of my stem plot, is going to go from 20 to 25. And it looks like I might have a 21, a 22, 23, and a 24 in there. So that's nice. So let's make the stems. All right, so first thing I'm going to do is I make this line here, which goes really good on some graph paper if you've got it. And then I write 20, 21, 22, 23, 24, 25, which should span the lowest to highest range of our data. So what I'm going to do is I'm going to add leaves. And what that looks like for 20, for example, is 2 8s, because there's a 20.8 and another 20.8. And that's it for 20. So I'm going to fill in the rest for 21 through 25. So what I've done for those is I've found all the values, for example, that had a 21 in the beginning, and I ordered the rest of the decimals from smallest to largest. So there was a 21.0, a 21.5, a 21.6, a 21.7, and a 21.9. And I did that for 22, 23, 24, and 25. So something else to notice, other than just putting everything in numerical order, is that I tried my very best, in my handwriting at least, to stack these digits on top of each other, because we want to see, all right, which ones have the highest values or had the most value. So for example, 22, there was a lot of head circumferences that started with 22, and 23 is a very close runner-up. So make sure that you're organizing these things. So the last thing we've got to do is add a key. Normally I like to stick my key on the right-hand side, but I didn't really leave myself a whole lot of options over there. So on the left-hand side it is. So our key says 23 with that line there, 5, is a player with a head circumference of 23.5 inches. So the second part of that example that we needed to take care of is describing the shape of the distribution and answering the question, are there any obvious outliers? Before we discuss that, I did want to show you a different way that you can create a stem plot. So this is what our stem plot looked like with 20 through 25 here, but if you've got a lot of numbers for one or more data points, you can actually split it up. And that's called splitting stems. So what you can do, and you can do this in a number of ways, it's really up to you. So there's 120 because there's only two 20s really, and then there's two 21s you could split it up into. They've got two 22s, two 23s, two 24s, and two 25s, if you so wish. That is one way that you can display that data, but this is well and good as well. So let's talk about the shape of the distribution. I'm going to talk about this one because we looked at it already. So what I would say is that it looks like this distribution is roughly symmetric. We've got one peak here at 22, and then it kind of just falls naturally to the side there, decreasing at a relatively symmetric rate. And with that being said, I don't see any obvious outliers because there's nothing that is drastically larger down here or drastically smaller as far as head circumference goes. So formally we would just say distribution of head circumference is roughly symmetric with a single peak on the 22-inch stem, and there are no obvious outliers. And before we wrap up this video on stem plots, I'm going to steal a couple words of wisdom from our book that I think are important. So first, there's no magic number of stems to use. Too many, too few might make it difficult to see your distribution's shape, depending on what it is, whatever the story is that you're trying to tell with that data, or whatever you're trying to figure out about that data. So if you just prefer to put every single number like we did, 20 through 25, and then however long those leaves go, you do you. If you want to split them up, also an option. It really depends on how much data you have. Second thing, if you do split stems, make sure that each of them is assigned an equal number of possible leaf digits, right? You want to be equitable there. And then when your data has too many digits, so you got really long decimals, sometimes you get more flexibility by rounding or truncating the data. Truncating is just when you chop off at the last digit, you don't even consider what comes after it to round up or down. That's truncating. Something else to consider is a back-to-back stem plot. So let's say that with that middle school resting pulse data, let's say you measured it before, right? So resting pulse. And then after, you can actually create a back-to-back stem plot. So the key here says that 8 line 2 is a student whose pulse rate is 82 beats per minute. So you might have data with 2 different variables that you want to represent. And the way that you read or even write one of these is that you take what we already know, right? So 6, 7, 8, 86, 87, 88, etc. is the after exercise. But over here, you look and it mirrors it. So the one closest to that 8, 82 is where we start. So it actually goes up as you go to the left, however you want to think of it. But you can actually display multiple variables using a stem plot. Quite handy. All right, that's going to do it for this video. Thanks for watching.